Have you ever looked up at the sky and marveled at the effortless grace of a bird soaring overhead or the incredible power of a rocket piercing through the atmosphere? Flight has always captured our imagination, pushing us to explore the boundaries of science and engineering. But how exactly do creatures and machines defy gravity and take to the skies? Today, we're going to unravel the mysteries of flight, diving into the fascinating physics that make it all possible. Let's embark on a journey into the natural world, where birds and insects have mastered the art of flying through millions of years of evolution. At the core of their ability to fly are three fundamental forces: lift, drag, and thrust. Understanding these forces is key to grasping how flight works. Lift is the upward force that counteracts the weight of the bird or insect, allowing it to rise into the air. But how is lift generated? It all comes down to the shape of the wing and how it interacts with the air. Wings are often designed with a special shape called an airfoil, which is curved on the top and flatter on the bottom. As the wing moves through the air splits at the leading edge and flows over and under the wing. The air traveling over the top of the wing moves faster than the air underneath. According to Bernoulli's principle, faster moving air has lower pressure. This creates a pressure difference between the top and bottom surfaces of the wing, resulting in an upward lift force. The angle at which the wing meets the oncoming air, known as the angle of attack, also plays a crucial role. By adjusting this angle, birds can control the amount of lift generated. A higher angle of attack increases lift up to a certain point. However, if the angle becomes too steep, the airflow can separate from the wing's surface, leading to turbulence and a loss of lift, a phenomenon known as a stall. Birds skillfully adjust their wing angles to optimize lift and prevent stalling during various flight maneuvers. Consider the hummingbird, a marvel of aerodynamic precision. Unlike most birds, hummingbirds can hover in midair by flapping their wings in a unique figure-8 pattern at incredibly high speeds, up to 80 beats per second. This motion allows them to generate lift on both the downstroke and upstroke, effectively balancing the forces to stay stationary. Their wings can rotate at the shoulder, giving them remarkable control and the ability to fly backward or sideways. On the other end of the spectrum, the albatross is a master of gliding. With its long, narrow wings spanning up to 11 feet, the albatross can exploit wind currents and updrafts to soar for hours without flapping its wings. This is known as dynamic soaring. By skillfully using the wind gradients over the ocean surface, the albatross minimizes energy expenditure, allowing it to travel vast distances across the ocean while expending minimal energy. Thrust is the forward force that propels the bird through the air, overcoming drag, which is the air resistance opposing its motion. Birds generate thrust by flapping their wings, pushing air backward to move forward. The muscles in a bird's chest, particularly the pectoralis major and supracoracoideus, provide the powerful strokes needed for sustained flight. The interplay between lift, drag, and thrust allows birds and insects to perform astonishing aerial maneuvers, from the agile turns of a swallow to the hovering of a dragonfly. Insects, too, showcase incredible adaptations for flight. The wings of insects like bees and butterflies are flexible and can twist and bend during flight. Some insects can beat their wings hundreds of times per second, generating lift through complex aerodynamic mechanisms that scientists are still studying. The study of insect flight has even inspired designs in micro-air vehicles and drones. Transitioning to human-made flight, airplanes operate on the same basic principles but with some key differences. Instead of flapping wings, airplanes have fixed wings and use engines to generate thrust. The wings are carefully designed to create lift as the plane moves forward, just like the wings of a bird. Engineers spend a great deal of time optimizing wing shapes to maximize lift and minimize drag. The shape of an airplane wing is critical. Similar to bird wings, airplane wings are curved on top and flatter on the bottom, forming an airfoil. This design leverages Bernoulli's principle, creating a pressure difference that results in lift. However, the wings alone aren't enough. The airplane must reach a certain speed to generate sufficient lift to take off. This is why airplanes have long runways, to build up the necessary speed. Control surfaces like ailerons, elevators, and rudders help pilots maneuver the airplane. Ailerons are located on the trailing edges of the wings and control roll, allowing the plane to tilt left or right, which is essential for turning. Elevators are on the horizontal tail and control pitch, making the nose of the plane go up or down, which is crucial for climbing or descending. The rudder, located on the vertical tail, controls yaw, which turns the plane left or right on a vertical axis, helping to coordinate turns and maintain stability. Engines provide the necessary thrust to propel the airplane forward. In propeller-driven planes, the propellers act like rotating wings, generating thrust by pulling or pushing air backward. In jet engines, air is drawn in at the front, compressed, mixed with fuel, and ignited. The hot exhaust gases expand rapidly and are expelled out the back, producing thrust. This is an application of Newton's third law of motion, similar to rockets but relying on atmospheric air for combustion. Modern airplanes are marvels of engineering, incorporating advanced materials and technologies to improve efficiency and safety. For instance, winglets, small vertical fins at the tips of wings, reduce vortex drag and improve fuel efficiency. Fly-by-wire systems use electronic controls instead of mechanical linkages, allowing for more precise and responsive handling. Now, let's explore rockets, which achieve flight in a fundamentally different way. While airplanes rely on the aerodynamic principles of lift generated by wings and the atmosphere to operate, rockets use Newton's third law of motion. For every action, there is an equal and opposite reaction. Rockets produce thrust by expelling mass at high speed in the opposite direction they wish to travel. This is achieved through the combustion of propellant, a mixture of fuel and oxidizer, which produces hot gases that are ejected out of the rocket's engine nozzle at tremendous speeds. The force of these gases rushing downward pushes the rocket upward. This reaction doesn't depend on the atmosphere, which is why rockets can operate in the vacuum of space. Unlike air-breathing engines like those on jets, rockets carry both fuel and oxidizer. This is necessary because, in space, there's no atmospheric oxygen to support combustion. Common rocket propellants include liquid hydrogen and liquid oxygen or combinations like kerosene and liquid oxygen. Solid rocket motors use solid propellant mixtures that burn upon ignition. Rocket launches are often staged, meaning the rocket sheds parts of itself as it ascends. The first stage provides the initial thrust to break free from Earth's gravitational pull and dense atmosphere. Once its fuel is exhausted, it's detached to reduce weight, allowing the next stage to take over with fresh fuel and engines. This process continues until the payload, such as a satellite or spacecraft, reaches its intended orbit or trajectory. Staging improves efficiency by discarding unnecessary weight, making it possible to reach higher velocities. The immense thrust required for a rocket launch is necessary to overcome Earth's gravity and atmospheric drag. The engineering challenges are significant, including managing extreme temperatures, pressures, and the structural stresses of high-speed flight. Rockets must also navigate precisely to reach their intended destinations, requiring sophisticated guidance systems. In contrast to rockets, airplanes and birds rely on the atmosphere to fly. Rockets, however, carry their own oxidizer, allowing them to burn fuel where there's no air. This fundamental difference highlights the diverse ways in which flight can be achieved. The development of rocket technology has enabled humanity to explore beyond our planet. From launching satellites that facilitate global communication and weather forecasting to sending astronauts to the International Space Station and probes to distant planets, rockets have opened up a new frontier. As we reflect on the wonders of flight, it's incredible to consider how both nature and human ingenuity have unlocked the secrets of the skies. From the delicate flutter of a butterfly's wings to the roaring ascent of a spacecraft, the principles of physics make it all possible. The study of flight not only satisfies our curiosity but also drives innovation across multiple fields, including materials science, engineering, and even biology. Flight continues to inspire us, pushing the boundaries of what's possible and inviting us to explore further. Whether it's studying the biomechanics of a hummingbird to improve drone technology or developing new aerospace materials to build more efficient aircraft, there's always more to discover. So next time you gaze upward, take a moment to appreciate the remarkable science that allows life and machines to soar through the air. The sky isn't the limit, it's just the beginning.